In this last session, we try to show you what happens when everything comes together. And this is the world of the secondary aerosols. Secondary aerosols are those who are not emitted directly by the sources, but they are formed in the atmosphere due to chemical reactions and macrophysical processes, or what we call aerosol dynamical processes. And I use the word aerosol dynamics here to avoid confusing it with cloud microphysics. Okay, so whenever I talk about dynamics, I don't mean the dynamic core. I mean the condensation, coagulation, nucleation, the processes that I will show you in a second. You remember the volume and number concentration and the equation. These are the prognostic equations that we solved, the continuous equation. And the terms which are in these red rectangles are those ones that I will discuss in the next couple of slides. And then you will have a hands-on experience with this. We have nucleation and coagulation. Basically, nucleation is when we have particles or molecules from the gas phase coming together and building stable clusters that are large and stable enough to become particles. This is nucleation. And one classic example is the nucleation of sulfate particles out of sulfuric acid in the gas phase and the water vapor. Okay. Then these particles collide with each other and also other particles, which we call coagulation. So here, the particle flow regimes matter. Okay, if my son is 6 years old, if he runs through these rows, he probably passes without hitting anyone. If I go through the rows, I hit every one of you, right? Because I'm too big. And he is a small particle and a big particle in an atmospheric flow. And this is really the regime that we talk about when we talk about particle flow regime. It really matters what are the conditions, like the mean free path of the air molecules compared to your particle size. And it shows your coagulation regime. If you are in a free molecular, like my son, which moves freely, or continue, like me, that I hit everyone. So this is the difference. And then we have the condensation that as I mentioned, it's basically condensation from the gas phase directly to the aerosol. And then we have also the partitioning between the gas phase and the aqueous phase. And this is done by the Hoshyaripour model, which looks at the thermodynamic equilibrium. And if certain species prefer to stay in the gas phase or prefer to go to the aerosol phase. And actually, that's it. This is the whole processes that we consider here. And why does it matter? And I told you, because we are dealing with the number and mass concentrations. We talk about composition, size, and morphology. And all of these properties will change due to macrophysical or aerosol dynamical processes. And this, to a large extent, determines, for instance, as I told you, if you have a coated or uncoated dust particle, this decides if it acts as a cloud condensation nuclei or as an ice nuclei. Or how much we had a discussion like black carbon. A coated black carbon particle is a much stronger absorber than the uncoated particle. So these are really details that matter. And this is a very simple, I have another level of complexity, but this is just one dimension. And this shows a little bit these processes and how different processes contribute to the size. We have on side the gas molecules, let's say nanometer scale, and then we go to, let's say, tens of micron to millimeter scale when we get to the hydrometeors or cloud droplets. From the gas molecules, we have nucleation, which means coming together, building particle, condensation, and equilibrium that brings the gases to the aerosol mode. This is usually contributing to the smallest part of the aerosols. First of all, nucleation is because we have very tiny particles forming at the beginning. We call them even ICON mode, nucleation mode, which is really a nanometer scale. But they very quickly grow to the ICON mode, which is what you see in this blue group here. Then they coagulate. Okay, they coagulate and they grow and come to the next mode, which is the accumulation mode. And the accumulation mode is also affected by the emissions. For instance, from dust, from sea salt, natural aerosols mostly contribute to accumulation mode and the coarse mode. This you see at the end. So the emission and sedimentation, of course, the removal affects these two a lot. One interesting aspect is that, well, and then when they get activated by as the cloud, condensation nuclei, or as ice nuclei, they go to the hydrometeors and they might be removed by precipitation. One interesting thing is that the flow from left-hand side to the right-hand side is usually dominant, usually. And this is why we said the middle one, we call it accumulation mode, because things accumulate there. From accumulation mode to the coarse mode, the physical moving due to coagulation is negligible because we have coarse mode or larger particles. They don't offer so much surface area for the processes we are interested in. So the accumulation mode has its name for a reason. And how do we do this in ICON art? We basically, I told you, now think about the other dimensions that I mentioned before. This is just the size. We have also the mixing state. Now, this figure shows you a little bit of how do we treat it in ICON art. We try to simulate it. Let me make this smaller. Can I bring it down here? Yeah. We try to present three mixing states. One is the soluble state. You see here sulfate, nitrate, ammonium, organics, primary and secondary organics, and water. On the other end, we have the insoluble particles. This could be black carbon or soot particles, dust, and volcanic ash. But these insoluble guys here can get coated by the soluble modes and generate a mixed mode. And if we combine 3 times 3, it gets us, if I can find my mouse here, yeah, it gives us 9 modes, combinations of different mixing states and sizes. Which one is useful for you for your application? It is always your decision, and your assumption, depending on your question. But this is only what is possible to do with the model. Once we have these mixing state and size combination, then for each species, you have to solve this kind of prognostic equation that is shown here. This is only the macrophysics part. I skipped everything from ICON and from other processes. Here you only see for the null and third moment, which are number and volume concentrations. You see the coagulation and nucleation. You see that in the first equation, coagulation, Ca appears 2 times. But if you look at the index of it, it's II and IJ. This means that either you have the coagulation within the same mode, particles in the same mode coagulate, or IJ is between two different modes with each other. So we call it intermodal and intramodal coagulation, okay? And then for the mass, the intramodal doesn't play a role because the mass of your mode doesn't change. This is why we see that here we only have the intermodal, and then condensation changes the mass, and nucleation, which also generates new particles. So generation of new particle, growth of the new particle means that when the particle grows at some point, they might also get shifted to a different mode. And Wait. Okay. Why? Oh, now this is this 3D representation that I was talking about. Look at the three modes on the first row that you see. You see the Aitken mode, accumulation, and coarse mode again with each of these curves basically. And then you see soluble, insoluble, and mixed mode. And what you can see is that we can have shifting and processes contributing to each mode. Generally, condensation, partitioning, and water uptake affects most of the modes. We can have coagulation between the sizes and mixing state modes. And we can also have two types of shifting. What you see here in the bottom here is basically the insoluble, which gets shifted to the mixed mode. And this happens when we have in a mode a certain threshold of soluble material. We have the processes ongoing, and I have dust, and then this dust mode uptakes, for instance, water or sulfate. When this the mass of this soluble part gets higher than 5%, we assume that it's now mixed or coated. So it goes to the mixed mode and then continues to grow and have fun over there. We have other process. The other type of mixing is here, when we have the growth of the particle and they get large and again go beyond the threshold in the diameter, they are shifted to a larger mode. And this happens in all of the mixing states, basically, because they all are affected by the coagulation. Okay? So what you see here, you see basically four names for the sizes, the black color here. I think this is an occasion that I can also introduce you the giant mode. This is what we usually assume for the largest mode of dust and sea salt, but this is not the giant mode that it's always referred to for these giant dust particles. For us, it's just a name convention that we say that it is larger than the coarse mode. So these are the four sizes that you can have. One important aspect, giant mode does not contribute to an aerosol or aerosol dynamics process because it's just too big to be important for such interactions. Okay.